Hi everybody! So today's video is going to be about Module 2, Task 2.2, and we're going to be focusing on several different learning targets today. Now you're going to notice that some of these learning targets are a repeat of the learning targets from the 2.1 video. The two big new ones today are really the first two that are listed here, which are I can write an explicit equation to model a linear function, and I can write an explicit equation to model an exponential function. Now, in our previous video, we sort of talked about what makes a function linear and what makes a function exponential. In this video, we're really going to focus now on connecting that to how we write equations, which is also going to be a review from Module 1. So we're kind of bringing a lot together here, and we're kind of connecting a lot of ideas. We are also going to continue making sure that we know how to graph a linear function and we know how to graph an exponential function. So we did review that in our last video. We're going to do that a little bit more in this video. And finally, we are going to continue our discussion of if a relationship, identifying if a relationship is discrete or continuous, which was a new idea for this module, and also identifying if a relationship is linear or exponential, which was a new idea for this module, but we did start talking about those two ideas in the previous video as well. So although there are a lot of targets today, the bottom targets here are really a review or kind of a reinforcement of something we've already done, and the ones at the top are where we're really bringing in something new, where we're connecting what we learned how to do in Module 1 with what we're learning how to do in Module 2. So, as a review, a linear function is the same thing as talking about an arithmetic sequence. So, if a sequence is arithmetic, we call it a linear function, and an exponential function is the same thing as talking about a geometric sequence. So, if a sequence is geometric, we call that function exponential. What I'd like to do before we kind of go through some practice problems today is review what recursive and explicit equations look like for these types of sequences. And the reason we're going to review this is that if we have a recursive equation for an arithmetic sequence, that's also going to be a linear function. So we're going to kind of connect what we did in Module 1 with recursive and explicit equations to what we're learning in Module 2, where we're now just calling them linear and exponential functions. So let's start with a recursive example. So if I was to write an example of a recursive equation for an arithmetic or linear function, I would say something like this: f of x, where f would be the output and x would be the input, output on the outside, input on the inside, is equal to, and then the next thing would be f of x minus 1. And it would be x minus 1 because we're looking at the previous term. Since this is a recursive sequence, we're going to, and for a linear function, our pattern is either going to be adding or subtracting. So an example would be something like plus 3. We know that this is linear because this is the common difference. And there is an adding pattern. Now, the second part of what goes with a recursive equation is that we're going to need a starting point. So our starting point here, I'm just making this up, would be something like f of negative 2 is equal to 7. And this would tell me start at 7 and then add 3 every time. Now, if I wanted to turn this recursive equation into an explicit equation, it would start the same way. So I would still have f of x, output on the outside, input on the inside, equals, then I would need my starting output value. So since the starting output value here is 7, my starting value here in the equation would be 7. Then my pattern, so since my pattern is plus 3, my pattern here would be plus 3. And then I would put parentheses with x on the inside. And then I need to decide, is that just x or does it need a buddy to get back to 0? Since my starting value here is negative 2, this equation would need a plus 2 by the x in order to get back to 0. So as a reminder, this is get the starting input back to 0. Now, I think what's really important is to realize that regardless of the type of equation, we can always see the common difference in both equations. We can see the common difference here at the end of the recursive equation, and we can see the common difference here in the explicit equation. Now, the common difference will always be multiplied by x. So even if we took this equation and we rearranged it a bit, and we put that 3 at the beginning, which is totally okay. We are allowed to rearrange it. The 3 is still what's being multiplied by x, and that is still the common difference in the equation. Now let's talk about exponential. So as a review of what an exponential equation would look like for a recursive, we would have f of x is equal to f of x minus 1. And as we talked about in Module 1, every recursive equation starts off the same way because we're always referring back to the previous term. But this time, the pattern would have to be multiplying or dividing. So I'm going to put times 3 here instead of plus 3. This would be the common ratio. Which is a multiplication pattern. It could also be dividing if this was going to be a geometric or exponential, which are the same thing. Our starting value can be the same number. F of negative 2 is equal to 7. Now, if we were to turn this into an explicit example, we would have f of x is equal to our starting output, which in this problem is 7, and then our pattern, which in this problem is times 3. And then we would need an exponent. And the reason we're going to have an exponent is because our pattern is multiplication. And we need to get our input back to 0. So since this starts with a negative 2, we would put a plus 2 here to get the input back to 0. Now again, we can see that common ratio in 2 spots depending on the equation. So the common ratio here would be whatever you're multiplying by. In this case, it would be times 3. All right, now let's take this and let's pull it all together. So I'm going to give you a scenario, and I'm basically going to ask you to do everything you could possibly do. We're going to make a table, make a graph, determine if it's linear or exponential, and explain how we know, determine if it should be discrete or continuous, and explain how we know. We're going to write a recursive equation, we're going to write an explicit equation, and we're going to use those equations to predict what's going to happen for a bigger number. So there's a lot going on here. This is going to be one big problem to connect all of our ideas. So the problem says a library is buying books to add to their collection. The books are shipped in boxes that contain about 8 books. So if we wanted to make this table, since the boxes contain about 8 books, one box would have 8 books. Then we can figure out how many would be in the other boxes by just adding. So we would do plus 8 here, and we would get 16. We would do plus 8 more, and we would get 24. We would do plus 8 more, and we would get 32. And then we could do plus 8 more, and we would get 40. Now we can also graph this information. So the inputs here would be boxes, which means I'm going to label boxes along the x-axis of my graph. And the outputs here would be books. So I'm going to label books along the y-axis of my graph. Then I'm going to graph my points. So I have 1, 8, which would be like right between the 5 and the 10. I have 2, 16, 3, 24, 4, 32, 540. Now, there are a couple things that I want you to notice here. We have an adding pattern, which means it's an arithmetic sequence. And our graph is a straight line, which makes sense because if we have an arithmetic sequence, our graph should be a straight line. So these things are all connected. And if, like, let's say, for example, you had an adding pattern, but when you graphed it, you ended up with a curve, then that would tell you that something went wrong because adding pattern should always give you a straight line. Now, we said in our previous video that whenever we have an arithmetic sequence, we're going to call that a linear function. So here I would say that this function is linear, and I would say my explanation is because the sequence is arithmetic. So the function is linear. So anytime you have an arithmetic sequence, it's going to be a linear function. Now, in this case, we're counting how many books there are. So if we have to think about should we connect the dots or not, I would go with no. And the reason I would go with no is because the number of books is something that you're going to count. It's not something you're going to measure like with a ruler or a measuring cup. So I would say that this is a discrete function because the number of books is something you count, not measure. Finally, let's write some equations. So a recursive equation here, I'm going to use, I'm going to use f of x as my variables. I don't want to use b because I would have to use b for both, and that would be really weird. So I'm going to say my recursive equation is f of x is equal to f of x minus 1, so back it up 1, so take the previous, and then add 8. My starting value here would be f of 1 is equal to 8, and I can see that in my table right here. There's my starting value. For my explicit equation, I would say f of x is equal to, and then I would say start with 8 and continue to add 8 each time. And then I would put parentheses with an x on the inside. Now, since my starting value here in the table is a 1, I would put x minus 1 here because I need to get back to 0. Finally, if I want to know how many books the library would receive in 25 boxes, in this case, because the number 25 is not the next number in the table, this table stops at 5, I would use the explicit equation because I don't know the previous value. So one of the things we talked about in our last unit and our last module was that if you know the previous number, the recursive is easier. I could just add 8. But since I don't know how many I had in box 24, it's going to be easier to use the explicit equation. So what I'm going to do is just take the number 25 and I'm going to replace the x in the equation with 25. So my new problem will say f of x is equal to 8 plus 8 times 25 minus 1. Now you can use your favorite calculator of choice. I think the online Desmos calculator is super convenient for something like this. There's also a built-in calculator on your Chromebook. I'm going to go ahead and use my handy dandy calculator here. And when I calculate that, I get 200. So the number of books after 25 boxes would be 200 books. And I'm just typing that in on my calculator to get that number. All right, let's try this one more time with a slightly different scenario. So it says a dose of 60 milligrams of medicine is given to a dog. The medicine breaks down so that each hour there's only half left in the dog's bloodstream. So it gives me two pieces of important information here. We start off with 600 milligrams. So at the beginning, our starting value is 600. It also tells me there's only half left after each hour. So that means that to get the next number, I would multiply by 1/2, which means I would get 300, multiply by 1/2 again, which would give me 150, multiply by 1/2 again, which would give me 75, and then multiply by 1/2 again, which would give me 37.5. So I'm using that pattern to fill in the rest of the table. Now my inputs here would be hours, so I'm going to write hours along the bottom of my graph. And my outputs here would be amount left, so I'm going to label the y-axis on my graph with amount left. Now I did that kind of quickly, but again, this is a review. We did this a lot in Module 1, so hopefully you're kind of seeing that we're connecting what we did in Module 1 with what we're now doing in Module 2. Now, if I graph these points, I have 0 and then 600. You know what? The labels on this graph are not correct. I do apologize for that. Let's label this 50, 100, 150, 200, 250, 300. I think the numbers just got cut off. They should have been like 10 times bigger. 450, 500, 550, 600. Oh, no, it's not that. It's me. I'm the problem. This should actually be 60 and then 30 and then 15 and then 7.5 and then 3.75. I'm the problem. I misread the number. It should be 60. Whew, I'm sorry about that, guys. Ignore what I just said. Okay, so now when we graph, we would have 0, 60. 1 would be 30. 2 would be 15. 3 would be 7.5, and 4 would be 3.75. Now, based on that graph, I'm seeing it looks like a curve, but since we're measuring medicine is not something you would count. It's something you would actually measure like in a syringe or in a measuring cup. So I'm going to go ahead and connect these dots because this is something that happens continuously. The medicine gradually breaks down. Now, when I look at my vocabulary here, I would call this an exponential function because since the pattern is multiplication, this is going to be a geometric sequence. So I would say since the sequence is geometric, the function is exponential. So a geometric sequence always makes an exponential function. We also can say that this is a continuous function because medication is something you would measure, not count like we did with books. You would count books 1, 2, 3, 4, 5. You would measure medication like with a syringe. Now let's write some equations. So my recursive equation, I'm going to use the variables A for amount left and H for hours. So I would have A of H is equal to A of H minus 1 and then times 1/2 because that's my common ratio. That's my pattern. I also would have the starting value A of 0 equals 60, and that would be in the first row of the table here. For my explicit equation, I would have A of H, again, it starts the same way, But then I set it up a little bit differently. So my starting value is 60 times 1/2, because that's my pattern. And now I need to use an exponent because we're multiplying. So I would have h, and then I need to get back to 0. Well, this table already starts at 0, so there's no adjusting necessary. It would just be to the h power. Finally, the problem says how much medicine is left in the dog's bloodstream after 12 hours. Again, if I want to know what's happening after 12 hours and I already knew what happened after 11 hours, I would use my recursive. But since I don't know what happened after 11, my table only goes up to 4, I'm going to go ahead and use the explicit equation here because I don't know the previous term. So I'm going to plug the number 12 into my explicit equation, which means I'm going to have A of 12 is equal to 60 times 1/2 to the 12th power. Now this is again a time when a calculator is going to come in really handy. So 60 times 1/2 to the 12th power is going to give me 0.0146. And this is going to be milligrams, which we usually abbreviate mg of medicine. All right, I apologize for kind of misreading the question here. Hopefully you kind of caught that mistake. It would just be 60, 30, set 15, 7.5, and then 3.75. I apologize for that. All right, that is it for our video today. Thank you guys so much for watching. I hope you have a great day, and I will see you for some practice soon.